You may be familiar with the ellipse as a kind of an oval shape. In fact, the ellipse is a very particular oval shape. The ancient Greeks defined it like this. First, you pick 2 points in the plane, and they're called foci, which is the plural for focus. So you pick these 2 foci, and you pick a distance a, which can be any distance that's long enough, and the ellipse is all of the points in the plane so that the distance from one focus to the point plus the distance from the other focus to that point is equal to twice the distance that you chose. We'll see why it's nice to have a 2 here in a little bit. So this is just an example of an ellipse. And if we draw the line segment from any point on the ellipse to the focus and to the other focus, if you imagine straightening these 2 line segments out and comparing them to the other point P over here, you'll see that the sum of each of the 2 distances on the right is equal to the sum of the 2 distances to the point P. In fact, if we put a point down here, maybe call it Q, the sum of the 2 distances to Q is also equal to the same as the sum of the 2 distances to P. Even if we put a point over here and call it R, the sum of the 2 distances to R is equal to the sum of the 2 distances to P and the sum of the 2 distances to Q. And that's what makes this particular oval shape an ellipse. Of course, now that we've defined an ellipse, it would be nice to have an equation for an ellipse. This is something that the ancient Greeks couldn't do because they didn't have coordinate systems. But to come up with an equation, the first thing we need to do is decide where to put our coordinate system. And one nice way to arrange the coordinate system is to put the origin exactly in the middle of the ellipse, just because of the symmetry of the ellipse. There's a center point in the ellipse, and the ellipse is symmetric across the line vertically through the center. And actually, the ellipse is symmetric across the horizontal line that goes through the center and both foci. And that sort of suggests arranging your coordinate system like this, so that you have the center at the origin of the coordinate system. The 2 foci are to either side of the center. The x-axis goes through the center and the foci, and the y-axis goes vertically. Now, one thing that's not totally obvious here is why is it that the foci why is it that you can write the coordinates of the foci as c, 0 and negative c, 0? So pause the video and think about that for just a minute. Why is it that you can write the coordinates of the foci as c, 0 and negative c, 0? So my explanation for why this must be possible is because the foci were symmetric, because we chose the center of the ellipse so that the foci are symmetric on either side of the center of the ellipse, that means we know that these 2 distances here have to be the same. I mean, we chose the center of the ellipse to be the midpoint between the foci. So these distances on either side of the origin have to be equal. And that means they're the same. That means the x-coordinates of the 2 foci are the same, except they're in opposite directions, and so they're actually negatives of each other. So if you call the one on the positive side c, then the one on the negative side must be negative c. Also, we defined this coordinate system so that the x-axis goes through the center of the ellipse and the 2 foci, and that means the y-coordinates of the foci must be 0. All right, so let's have a look at our next issue with this ellipse. So it turns out that if you slide the point on your ellipse all the way to the left, it gives you a way of understanding what this number 2a really means. And it turns out that the length 2a is actually the distance from this far left point on the ellipse to this far right point on the ellipse. So pause the video and see if you can come up with an explanation for why it is that the distance 2a is from this far left point to this far right point. Okay, so remember what 2a actually has to do with the ellipse. The way that 2a is involved in the definition of the ellipse is that the distance from f1 to p plus the distance from f2 to p is always equal to 2a for p on the ellipse. Well, if we slide the point P all the way over to the left here, then that means the distance from F1 over to P plus the distance from F2 over to P, when you add those together, you have to get 2a. But look, this distance from F1 to P, if we just slide it over here, it perfectly fills in the gap from F2 to the rightmost point. And the reason that it has to work that way is because the ellipse is completely symmetric across the y-axis. Right? The way that we set up the coordinate system together with the symmetry of the foci is what makes the ellipse perfectly symmetric across the y-axis. So the distance from P to F1 perfectly fills in the gap from F2 to this far right-hand point. And remember, this entire distance is 2a. So that means the distance across the ellipse is 2a. Just to give some things some names, these far left and far right points, these are called vertices. That's plural for vertex. And the distance 2a is called the major axis. And the distance a, that's the distance from the center of the ellipse to one side of the ellipse, or to one vertex of the ellipse. And the distance a is called the semi-major axis. Semi because it's half of the major axis. Okay. So we figured out that A is the semi-major axis by sliding the point P all the way to the left of this ellipse, but it seems like there's one other special place on the ellipse, and that's at the very top. Let's see what we can learn by sliding our point on the ellipse all the way to the very top. So somewhere in this diagram is the length A. We know that the length A is the distance from the center to the right vertex on this ellipse, but if we slide the point P all the way to the top, we get this triangle, and some side in this triangle is actually the length A. It's not the bottom side, because the bottom side is the distance from the origin to the focus F2, and we call that distance C. So it's one of these other two sides. Which of these two sides is the length A? Pause the video and see if you can decide for yourself. Okay, well remember that the distance from F1 to P plus the distance from F2 to P has to be 2a. Well, what are those distances in this diagram? The distance from F1 to P is this left diagonal line, and the distance from F2 to P is this right diagonal line. And those two are supposed to add up to 2a, but they're the same length, so a is just one of them. That means A is this hypotenuse in this right triangle here. And then I suggested that we call this vertical side B. Well, just like A is the distance from the center to the right-hand vertex, B is the distance from the center to the top vertex. And so B is called the semi-minor axis. And the distance from the top to the bottom, that's the short way across the ellipse, is 2b, and that's the minor axis. And it's minor because it's smaller than the major axis. Okay, so hiding inside of every ellipse is this right triangle where C is the focal distance, C is one side, the semi-major axis A is the hypotenuse, and the semi-minor axis B is the other leg of the right triangle. Of course, I hope you have the instinct whenever you see a right triangle to write down the Pythagorean theorem. And in this case, it says that b squared plus c squared equals a squared. It's a little funny to have the names for the sides set up this way so that a squared is by itself in the Pythagorean theorem. But if you just remember that a is the semi-major axis, which when you picture an ellipse, the semi-major axis is the longest piece, you won't get confused about which side is the hypotenuse in the Pythagorean theorem. All right. So at this point, we have enough information to finally write an equation for the ellipse. So go ahead and pause the video and see if you can write a formula for the distance from F1 to P and a formula for the distance from F2 to P. All right, so for each of these distances, so for the distance from F1 to P, remember P is some point on the ellipse, so its coordinates are going to be variables because P can move around the ellipse. But F1, that was the focus to the left of the center of the ellipse, and its coordinates were -c, 0. And so for the distance from F1 to P, we can just use the distance formula. That's the difference in x coordinates, so x minus -c, that's x plus c, squared, plus y minus 0 squared, so that's just y squared. All right, and then we can do the same thing for the distance from F2 to P. Right, P is, as before, it's still x comma y. But F2 is the focus to the right of the origin, and that was c comma 0. And so now we can use the distance formula to find the distance between these 2 points. It's the square root of x minus c squared plus y minus 0 squared. All right, these are the pieces we need to write an equation for the ellipse, so go ahead and write your equation of an ellipse. Okay, let's write the equation. We have these 2 distances, and remember that the equation of the ellipse is that the sum of these distances has to be 2a. So that means the square root of x plus c squared plus y squared, so that's the first distance, plus the second distance, which is the square root of x minus c squared plus y squared. That has to equal 2a. And that's it. That's an equation for the ellipse. But it's not very emotionally satisfying. It seems like a bit of a mess. In particular, maybe it's a surprise that those square roots are there. So when I see something like this, my first instinct is, let's see if we can get rid of the square roots. So see if you can get rid of the square roots by maybe creatively rearranging this equation, and I mean at some point you're going to have to square something to get rid of the square roots. So give it a try and see if you can get rid of those square roots. Okay, let's get rid of these square roots. We could square it as it stands, but I'm going to move this part to the right first. So square root of x plus c squared plus y squared, and the square root goes all the way over to here, equals 2a minus the other square root. So square root of x minus c squared plus y squared. Okay, now we can square both sides of this equation. The left-hand side is no problem because the square just undoes the square root, and we get x plus c squared plus y squared. But the right-hand side is going to be a bit of a mess. So what you want to do is just keep your eye on these 2 pieces, because we're squaring a binomial here. And we know how to square a binomial. It's first part squared plus twice the product plus second part squared. So first part squared, 2a squared, that's 4a squared, okay, plus twice the product. The product is going to be negative because of that minus sign there. So twice the product, 2 times 2a times the big square root. So that's 4a times the square root of x minus c squared plus y squared, all right, plus the square of the last piece. And this negative in the middle gets squared as well, and so that's why it's still a plus right here. So squaring this last piece just gets rid of the square root. So we get x minus c squared plus y squared. All right, now I can see right away that this y squared is going to cancel that y squared, so we can subtract y squared from both sides. And I also see that if we multiplied out these parts that have x's and c's all squared, some of that is going to cancel as well. So let's multiply all that out. We get x squared plus 2cx plus c squared equals 4a squared minus 4 times a times the square root of x minus c squared plus y squared plus, and now we're going to multiply this stuff out, x squared minus 2cx plus c squared. And sure enough, some stuff does cancel. We can subtract c squared from both sides. We can subtract x squared from both sides. All right, that's looking pretty good. Also, look, we have two terms that have c times x. So let's gather those together by adding 2cx to both sides of this equation. We get 4cx equals 4a squared minus 4a times the square root of x minus c squared plus y squared. Okay, so we got rid of sort of half of the square roots. There's still a square root left, but all we have to, when there's only one square root left, all you have to do to get rid of it is isolate this square root piece and then square both sides. So let's do that. So let's see, I guess I will subtract 4a squared from both sides, just to isolate that, the square root part. So minus 4a squared plus 4cx equals negative 4a times the square root of x minus c squared plus y squared. And now finally we're in a position to square both sides. And this will get rid of the last square root. So on the left-hand side, remember we're going to do first piece squared plus twice the product plus second piece squared. So we get 16a to the fourth minus, so 4 times 4 is 16, but twice that is 32a squared cx, bit of a mess there, plus, now last part squared, 16c squared x squared equals, on the right hand side we need to square this and square this, so 16a squared times x minus c squared plus y squared. Of course, before I did all this squaring, I should have gotten rid of those factors of 4, but we can get rid of the factors of 16 now. So this is gone, this is a 2, this 16 is gone, that 16 is gone. Okay. Now, again, it looks like if we multiply all of this stuff squared out, there might be some things that simplify. So let's see what happens. So we get on the left-hand side a to the fourth minus 2a squared cx plus c squared x squared equals a squared times, so we have x squared minus 2cx plus c squared plus y squared. Okay, so now I see that if we distribute the a squared, we're going to get some similar terms here that might simplify. So looks like we're going to have to distribute this a squared. A to the fourth minus 2a squared cx plus c squared x squared equals a squared x squared minus 2a squared cx plus c squared a squared plus a squared y squared. Okay, and it looks like this middle term, the a squared cx term, we can add that to both sides to cancel those out. All right. Now, there are some pieces of this that have variables, genuine variables, x and y. That's these parts. And there are some parts that just have constants. That's the a to the fourth and the c squared a squared. Let's get all the constants to the left and all of the variable parts to the right. So it looks like we need to subtract c squared a squared from both sides. And we need to subtract c squared x squared from both sides. When we do that, we get a to the fourth minus c squared a squared equals, and on the right-hand side, a squared x squared minus c squared x squared. So this part canceled. So plus a squared y squared. All right. Now, to me, it seems like the x squareds, I see that there's a common factor of x squared here. So I kind of want to factor those out. And also I see there's a common factor of a squared here. So let's also factor that out. So we get a squared times a squared minus c squared equals, and then on the right hand side we're going to factor out that x squared. We get we get a squared minus c squared times x squared plus a squared y squared. Okay. Well, look, that this a squared shows up on both sides, and this a squared minus c squared shows up on both sides. So it'll actually simplify things if we divide everything, both sides of this equation, by a squared times a squared minus c squared. So on the left-hand side, that's just going to leave 1. On the right-hand side, when we look at the x squared part, the a squared minus c squared cancels, and we're going to get x squared over a squared plus, and then for the y squared term, the a squareds are going to cancel, and we get y squared over a squared minus c squared. All right, so there's the equation of the ellipse. But wait a second. You might recognize this here. So take a second to go back to the previous diagrams on this handout and see if there's some better way we could write a squared minus c squared. Okay, so if you remember way back above when we slid the point on our ellipse to the top of the ellipse, we found that the semi-minor axis b squared plus the focal radius c squared was equal to the semi-major axis squared. So if you rearrange this, you get b squared equals a squared minus c squared. That means this denominator under our y squared is actually just b squared. So that makes the equation for the ellipse 1 equals x squared over a squared plus y squared over b squared. And that's it. So that's the usual way that people write the equation of the ellipse. And what makes this so nice is, if you know this, if you have this equation, you can graph your ellipse very quickly because the semi-major axis is right here. It'll show up squared in your equation, but it's the square root of this denominator is a, so you can just go out a either side to minus a and plus a. And then the radius in the y direction is just the square root of this denominator, so you can go up b and down b. And then the ellipse is just the sort of oval shape that fills this in. Of course, it's a very specific oval shape, but to just get an idea of what the ellipse is, you can sketch this oval. All right, so now that we have an equation for this ellipse, go ahead and work on the other problems on this handout and see if you can come up with equations for your ellipses and come up with graphs for your equations. Okay, let's have a look at this one. Let's find the x and y-intercepts of this ellipse. So to find the x-intercepts, remember, to find the x-intercepts, you just plug in y equals 0. And that's going to give us x squared over a squared plus 0 over 4 squared. Sorry, this a squared is 16 in this example, equals 1. So this becomes x squared over 16 equals 1. But then we can just find x. Multiply both sides by 16. You get x squared equals 16. And then take square roots. X is plus or minus 4. And that's for the x-intercepts. Now we can do the same thing for the y-intercepts. To find the y-intercepts, we're going to plug in x equals 0. And that gives us 0 plus y squared over 4 equals 1. So this 0 doesn't really add anything. So now we can multiply both sides by 4. Y squared equals 4. And then take square roots. Y is plus or minus 2. So that means the x-intercepts are going to be plus or minus 4, 0. And the y-intercepts are 0, plus or minus 2. All right, pause the video and work on the next problem on your own. Okay. Now let's sketch a graph for this ellipse. Now what we saw in the last example is, we know that a is the square root of this number over under the x squared, so that's 2. And we know that b is the square root of this number that's under y squared, so it's going to give us 3. And in the last problem we saw that once you know the radius in the horizontal direction, your x-intercepts are just going to be plus or minus that radius, 0. And your y-intercepts, if you know the radius in the y direction, your y-intercepts are 0, plus or minus that radius in the y direction, so 0, 3. So we can plot these intercepts, minus 2 and plus 2 in the x direction, and minus 3 and plus 3 in the y direction. And now that we have these plotted, we can sketch our ellipse. It's going to look something like this. Of course, a perfect ellipse has perfect reflection symmetry across the y-axis and the x-axis, so this isn't perfect, but it's not too bad, I guess. All right, pause the video and work on the next problem. All right. So let's find a formula for C, which, remember, C is if your foci are along the x-axis like this. So if these are your foci, which means your ellipse is going to be something like this. C is the distance from the center of the ellipse to one focus. So let's find a formula for C. Well, remember, in every ellipse, we said there was this right triangle hiding here. And C is the bottom side, A is the hypotenuse, and B is the vertical side. That means B squared plus C squared equals A squared. But we can solve this for C. So subtract B squared from both sides. C squared equals A squared minus B squared. And then we can take a square root. C is the square root of A squared minus B squared. And I've chosen the positive square root here. I'm ignoring the negative possibility because C is a geometric distance, so it has to be positive. So we can discard the negative possibility.